So now let's look into the practical uses of chi-square distribution, because we know the history of chi-square distribution and we have built a chi-square distribution from the scratch for hair color categorical variable. Now we will look into the practical uses of chi-square distribution, how a data scientist uses it. Basically, that's what now we do. So the chi-square distribution is a probability distribution that is commonly used in statistical inference, hypothesis testing, and machine learning. There's three important categories where we use it. So, statistical inference, hypothesis testing, and machine learning. So, it's a continuous probability distribution that arises from the sum of squares of independent standard normal random variables. Of course we have done all those things, but still when I reiterate these things you might get some confusion. So it's a continuous probability distribution that arises from the sum of squares of independent standard normal random variables, whatever we have did before, summing of squares of independent standard categories. That's what it's telling. Okay, now let's see. So the chi-square distribution is often used in many ways in data science. One of them and widely used one is goodness of fit. So the chi-square distribution can be used to test whether an observed frequency distribution of categorical data fits a certain theoretical distribution. So this is known as a goodness of fit test. Goodness of fit test. Then test of independence. The chi-square distribution can be used to test whether two categorical variables are independent. This is known as a test of independence. Then test of homogeneity. The chi-square distribution can be used to test whether the distributions of a categorical variable are homogeneous across multiple groups. This is known as the test of homogeneity. Then we have a confidence interval or variance. The chi-square distribution can be used to calculate confidence intervals for the population variance of a normally distributed population. Then we have principal component analysis, very important, PCA. So the chi-square distribution is used in PCA to calculate the eigenvalues of the covariance matrix of a set of variables. So in machine learning, the chi-square distribution is often used with the feature selection and dimensionality reduction. Very, very important. Very, very important. In machine learning, the chi-square distribution is often used in feature selection and dimensionality reduction. So it can also be used to assess the goodness of fit or fit of a model, or to test the independence of features in a data set. So overall, the chi-square distribution is a fundamental distribution in statistics that has a wide range of applications in hypothesis testing, statistical inference, and machine learning, etc., etc. So what we will do is we'll take some simple examples to understand how we can leverage the power of chi-square distribution. Okay, so let's get into this one here. Yeah. So imagine you are flipping a coin and want to see if it is a fair or not. Okay, that's what my target. So if it has an equal chance of landing on heads or tails, so to do this, so we have to determine a coin is fair or not. So now, to do this, you might flip the coin a bunch of times and count how many times it lands on heads versus tails. If the coin is fair, you would expect to see about the same number of heads and tails or many flips. However, if the coin is biased towards one side, you might see more of one outcome than other. Correct? But the chi-square distribution can help you determine whether the difference between the expected and the observed outcomes is due to chance or whether there is some underlying bias in the data. Shiv. That's how your chi-square distribution helps. Okay. So when you test it for this thing, we have to determine a coin is fair or not. For that, you will flip a coin. You will flip a coin multiple times. Okay. So then you will record observed values, and obviously you have thought something. So this one you will have some hypothesis with you. Your that hypothesis would be maybe getting coin head getting heads more times or tails more times. That's your hypothesis. Then you'll have the expected values also. So now you have observed values, and you also have a hypothesis. That's the expected values also. So when you have an observed values and expected values, you can use the chi-square distribution, and that will help you determine whether the difference between the expected and observed outcome is due to just chance, because it depends. No, there are a lot of other factors also which affect. So that's the reason to basically to confidently to tell that you need a chi-square. So here, the chi-square distribution help you determine whether the difference between the expected and observed outcomes is due to just a mere chance or whether there is some underlying bias in the data. So it does by how it will do. It does. So chi-square will comes into the picture, and then it takes the observed values and expected values, and using that it will do so it does this by using respective calculation. So it will calculate the value. It will calculate a value that measures the difference between the expected and observed outcomes, and then comparing that value to the probability distribution. That's the step one. And then once you got your score, or once you got your chi-square statistic, then that one will be comparing the that value to a probability probability distribution that tells you how likely is how likely it is to see that value if the data were truly random. So that's it. For example, if you flip a coin 100 times, let's take it as 100 times. That's the trial. 100 times and expect to see expected. So my expected values for heads is equals to 50, and for the tails is equals to 50, because my hypothesis is this is a fair coin. But actually observed values that we got for heads is equal to 60, and for the tails it is equals to 40. So now we can use the chi-square distribution to determine whether this difference is significant or just due to chance. So the distribution will tell you the probability of seeing a difference as large as or larger than one you observed. So assuming that assuming the data were truly random, if this probability is very low. So once you use the chi-square statistic, then we'll get the probability. If that probability is very low, then maybe lesser than 5 percentage. If it is lesser than 5 percentage, we may conclude that the coin is biased towards head. That's it. You may conclude that the coin is biased towards heads. So that's it. So in summary, the chi-square distribution is a tool used to analyze whether the observed data is significantly different from what you would expect to see by chance, and can be used in a variety of applications such as testing the fairness of a coin or analyzing the results of a survey. Very important. Analyzing the results of a survey or comparing the performance of a different machine learning model. Very, very important. Comparing the performance of the different machine learning models. Okay, and we will look into the one more example as quick as possible. I know it's too much explanation for the chi-square, but it's very, very important. That's the reason I'm taking this much of time. I hope you understand why I'm taking this much of pain. So another example. Sorry. So let's say we have a data set of 500 students. So data set of 500 students. So, and we want to test whether there is a significant difference between the observed and expected proportions of students who pass an exam. That's it. So now what we want to test is we want to test whether there is a significant difference between the observed and expected proportions of students who pass an exam. That's it. This is what we want to test. It's similar to that. So now for that, so our expected value, we expect that about, so our expected value proportion is equals to 60 percentage. So then expected frequency would be is equals to 60 percentage times obviously total number of students 500. And similarly then to test this hypothesis, so this is our hypothesis. Let me write it down here simply. So this is my hypothesis. So I expect that 60 percentage of students will pass. Let's see what's going to happen. So then to test this hypothesis using chi-square distribution, we have to perform the following steps. Let's begin with one by one. So step 1 in this, divide the students into two groups. Those who passed the exam and those who did not. Okay. Then step 2, calculate the observed proportion of students who passed the exam by dividing the number of students who passed by total number of by dividing by the number of students who passed the total number of students. Okay, so dividing the number of students who passed the exams by total number of students. So once that is done, so we will have our expected proportion of students who pass the exam that we have decided on top. That's our frequency, and then we got our observed frequency, observed proportion also. Now let's calculate. Our observed proportion is, let's take the total number of students who passed and failed by multiplying the expected proportions. The total number of students is this. So our observed proportion, let me check. So observed proportions, if I take observed proportion of maybe 50 percentage, that's fine. Yep. So now once this is done, so you got your observed proportions, you got your expected proportion both, and now it's time to calculate the chi-square statistic. That's it. So step 4, calculate the chi-square statistic using the formula. That is, subtract expected from the observed, and then square the result and divide it by the expected. So once you calculate that, you will get your chi-square statistic. So let me put the chi-square statistic is equals to something. Then you should know your degrees of freedom. So we have to determine our degrees of freedom. That's very important. Degrees of freedom is nothing but, let me put it into step 5. Of course it should be done before only, that's okay, I forgot to do. So determine our degrees of freedom, that is equals to number of categorical categories minus 1. So here we have only 2 categories minus 1, so 2 minus 1, that is equals to 1. So our degrees of freedom is 1. So now let's look up at the critical value from the chi-square. So step 6 is to look up at the critical value from the chi-square distribution table with df is equals to 1 and a chosen level of, I want to go for the level of significance of 5%. Level of significance of 5%. So let me see now. So I have this table here, which is a chi-square table. Yeah, it's taking some time, just a minute. Yep. So we got our degrees of freedom is 1 on rows. On first column you have your degrees of freedom, as a columns you have your level of significances. So now the areas given across the top are the areas to the right of the critical value. To look up an area on the left, subtract it from 1 and then look it up. That is 0.05 on the left is 0.95 on the right. Okay, that's what they are telling, how to interpret these values. So the values that are given for us are right of the critical value. These are all right side of the critical values. Okay, if you want to get it for the left side, then you have to subtract the respective value from 1. That's it. Okay, so now I got my degrees of freedom and I got my level of significance. I want to go with the level of significance of 0.05 and degrees of freedom and come down. So this is what my value is gonna be. So now, yeah, so okay, it's taking some time still. Notebook saved. I hope it's ready now. Yeah, it's ready. It's ready now. So now for this, the value that I got, so now I will take up this value. For example, I have take up this value. The value that I got is 3.84, correct? So my critical value, so critical value from chi-square distribution table with df is equals to 1 and level of significance is equals to 0.05, then the critical value is 3.84. So this is what I got. So 3.84. Since the chi-square statistic is less than the critical value, so what's my chi-square statistic? I forgot to put it here. So my chi-square statistic is equal to 0. So let me put it here. So my chi-square statistic that I have calculated is 0. So now chi-square, so my chi-square statistic, which is 0 lesser than critical value, which is 3.84. So what I have to say is we cannot reject the null hypothesis and conclude that there is no significant difference between the observed and expected proportions of students who passed the exam. So with this, we are able to accept the null hypothesis with a proof or with a solid support. So in this example, the chi-square distribution helped us determine whether the difference between observed and expected proportions of students who passed the exam was significant or due to chance. So it's important to know that chi-square test assumes that the data are independent, random, and come from a large enough sample size. And this is what is a chi-square distribution for a data scientist.